So today's lecture is basically math. We're going to talk about the math skills that you're going to need to do the rest of the lectures in. The math itself that we do is not difficult. The most difficult math we do is solve for x. If a times b equals 7 and a is 2, what's b? It's easy algebra. But if you have not done algebra, no algebra is easy for you. I think algebra is a prereq to get in this class, but obviously some people may have taken it last semester, some people may have taken it years ago. Not being able to do that algebra is going to be a big hindrance to you. If you struggle with that, I would work on getting yourself back up to speed on that. Because you can set up a problem perfectly fine, but quite often I see people set it up and then they say x equals such and such and they're nowhere close. Okay? It's just a matter of doing the algebra. I think Susan can help you with algebra if that's something you struggle with. When we do it in here, I have to assume that you know what's going on. Okay, I'll kind of walk you through it, but you've seen the learning objectives for the class. We unfortunately don't have time to go over how to do algebra. If you struggle with it, you can contact me outside of class. I'll certainly help you then. But we don't have enough time to really go over it hardcore in here. So, with math, not only are there numbers, but when we do math and science, there is always a unit. And you have to put the unit so that when you tell the number to someone else, they know what you're talking about. This is from quite a while ago now, but in 1999, NASA lost a Mars orbiter because one team used inches and one team used centimeters, and they didn't convert correctly. And so they literally lost a $125 million Mars orbiter because of units. Okay? When you give me an answer on a question, you have to have units. If it says, how long is such and such, and you say 5, you're going to lose points. You have to have units. I need to know whether you have the grasp of the units. Is it 5 meters? Is it 5 feet? Is it 5 centimeters? There are only 2 things the entire semester that are coming to mind where you can give me a number answer and a math problem that does not have a unit. And they're both at the very end of the semester. So you always want to get in the habit of when you give me an answer, make sure you give the units. Most of the units we use in science are based on this international system of units, or the SI units. Some of these units are things you're familiar with, some things you're probably not. Most of them are the metric system. So for length, the SI unit is a meter, mass is kilogram, volume is liter, and then time is seconds. That makes sense to you. Temperature is kelvins. Metric you normally think of as Celsius, but in science we use kelvins. And that'll become clear why once we actually start using it. And then the last one here, we won't even brush that until maybe a month or so from now. But if we're talking about the number of particles of something, we use something called the mole. And with these SI units, we add prefixes to them. We have meters, you know centimeters, you know millimeters, you know kilometers or kilometers. The only difference between them when you write them out is they are meters with a prefix. And the prefix changes that unit by factors of 10. So in this table, we have different prefixes. In meter is this line. So everything above that line is bigger than a meter. Everything below that line is smaller than a meter. Each of these prefixes has abbreviation, like centimeter, it's cm, that's centi, the little c, and then you put the m for centimeter. These are just the most common ones. There are prefixes for pretty much every factor of 10. So centimeter says it's 10 to the negative 2. 10 to the negative 2, if you put that into your calculator, it's going to spit out 0.01. 10 to the negative 2 is 1/100th. So 1 centimeter is 1/100th of a meter. That means that there are 100 centimeters in a meter. A millimeter is 10 to the negative 3rd. That's 1,000. There are 1,000 millimeters in a meter. Going up the other way, a kilometer is 10 to the positive 3rd. That means that it is 1,000 times larger than a meter. So 1 kilometer equals 10 to the 3rd meters, which is 1,000 meters. Eventually, you'll get in the habit of knowing which are smaller and which are larger, but at this point, I would really spend time focusing on them. Most of the units that we see are going to be centi, milli, or kilo. These other ones, you're probably not going to run into all that often. On the cheat sheet that you will have for every quiz after today's, you won't have it for today's because there's a periodic table on the back, but there's a table of these prefixes. And it says a mega is 10 to the 6th, and it says that is 1 million. So while you don't have to remember these conversion factors, they'll be given to you in this table. And so you need to be comfortable using a table that looks like this. If you can use a table like this, you don't have to remember any of these exponents. Okay? Most likely, the centi, milli, and kilo, in a couple of weeks, you'll have them memorized just by using them a number of times. But they are here. They go everything from a iota, which is 10 to the 24th, a septillion, down to a iocto, which is 10 to the negative 24th, and 1 septillion. You won't need that, but you will run into these some as we go. So this table here is for meters. Okay? I'm going to flip to the next slide, and it is for grams. If I flip back and forth, what's changing? The only thing that's changing is meters to grams. These prefixes you can put on anything. You can have a centigram. You can have a centiliter. You know, you probably hear milliliters and little liters all the time, but there are centiliters also, and kiloliters. Any of these units we're dealing with, you can put a prefix on to change it by a factor of 10. So we talked about matter last week. And we said matter is something that takes up space and has mass. We did not define mass. Mass is just quantity of matter. It's very, very similar to weight, but it is not technically the same as weight. Weight is influenced by the strength of gravity. Let's be optimistic and say I weigh 150 pounds. If I go to the moon, I am no longer 150 pounds. That 150 pounds represents the gravitational force between me and the planet or the moon that I'm standing on. That represents the force that the floor is exerting on me to hold me up. Because the gravity on the moon is much weaker, there's less gravity there, and so there's less force pulling me into the moon. So I weigh less on the moon. But mass measures the amount of matter. There's nothing there about gravity. If I go to the moon, I'm going to be made up of the same amount of matter as I was on Earth. And so my mass will not change on the moon as compared to the earth. So, in science, we use mass, not weight. Because weight always depends on where you are. Mass does not. The SI unit of mass is grams. When you work in the lab, a gram is a type of quantity that you're going to be using. Okay? This thing here probably weighs maybe 50 grams. Okay? 1 gram is a tangible amount. Okay? If you're working with pharmaceuticals, a pill of aspirin is about 325 milligrams, which is the same as about 0.3 grams. To measure mass, we measure it on a balance. Okay? The word balance comes from the old way they used to do it with scales. Literally a balance. You have to balance the unknown with the known. Now, what you and I would normally call a scale, electronic scale in the lab, is technically called an electronic balance. Okay? In a lab, we'll use the electronic ones, and then I think next week you will have to, at least for one day, use an old school type balance. Okay? This says a salt crystal is about 50 milligrams. That's a pretty big crystal. That's not like a table salt, that's like the chunks that are in the sea salt. So if a salt crystal is 50 milligrams, how many milligrams are in a gram? Let me go back to this. How many milligrams are in a gram? A 1,000. Right. A milli is 10 to the negative third. You put that in your calculator, it's going to spit out 0.001, which is 1/1000. Another way to kind of figure that out in your head is think 10 to the positive 3. You put that in your calculator, it's going to give you 1,000. And if 10 to the positive 3 is 1,000, 10 to the negative 3 is 1,000th. Okay? Then where you have to think about is, does that mean if milli is 1,000, are there 1,000 milliliters, or sorry, 1,000 milligrams in a gram, or are there 1,000 grams in a milligram? You need to remember, things below this line are smaller. If you're smaller, that means it takes more of you to equal something bigger. And so, if a milligram is smaller, the milligram is smaller than the gram, you're going to need a whole bunch of these to weigh the same amount as that. Does that make sense? Mm-hmm. So stop and think about it. If I figure out which one is smaller, that number must be larger. And so there must be 1,000 milligrams to equal 1 gram. A person is about 70 kilograms. So if you get into something bigger, it's no longer really convenient to use grams, and so we go to kilograms. How many grams are in a kilogram? 1,000. Kilo is 10 to the positive third, and so there are 1,000 grams in a kilogram. A kilogram is larger, which means the gram number must be larger. So there are 1,000 grams in 1 kilogram. How many kilograms are in a gram? How many kilograms are in a gram? You said there are 1,000 grams in a kilogram. Let's go the other direction. How many kilograms are in 1 gram? 0.001. 1/1000. You can flip back and forth. There are 1,000 grams in a kilogram, so there is 1/1000th of a kilogram in a gram. Next we can talk about volume. Okay? We're not going to do anything too spectacular with volume in here. Volume is the amount of space that something takes up. If you have a box, probably learned in high school, maybe sooner, length times width times height. If you have 3 dimensions, multiply them together to get your volume. If we're dealing with solids, the unit we normally use is cubic centimeter. And that cubic centimeter comes from the fact that these 3 dimensions would be in centimeters. And so you get centimeters times centimeters times centimeters, which is centimeters cubed, which we call cubic centimeters. A cubic centimeter is also called a cc. cc just stands for cubic centimeter. We have this box. What is its volume? It says that side is 2 centimeters, and it specifies that this box is a cube. 8. It's just, because it's a cube, all the sides are the same length. So we have 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. You can also put in your calculator just 2 to the 3rd power.
I'm sorry, not just 8 centimeters, right?
8
Centimeters.
cubic centimeters,
Oh, okay.
or centimeters cubed. Right. The volume of the cube is 8 cubic centimeters.
Can you put cc's instead of cm?
Yeah. If we're dealing with liquids, we don't normally use cubic centimeters. We normally use milliliters. But, very conveniently, 1 cubic centimeter is exactly equal to 1 milliliter. They're interchangeable. Cubic centimeters, cc's, and milliliters are interchangeable. Okay? But, based on convention, what we normally do, for solids we use cubic centimeters, for liquids we use milliliters, and because doctors are doctors and they think they can make whatever rules they want, they use cc's for liquid medicines. Okay? cc's are cubic centimeters, which really should be used for solids, but they're doctors, so they use them for liquids. How many milliliters are in 1 liter? 1,000. Milli, the lowercase m, is 10 to the negative 3rd, which is 1/1000. A milliliter is smaller than a liter, and so the number on the milliliter must be larger. So 1,000 milliliters equals 1 liter. So let's do some conversion. We get 25 milliliters. We need to convert it to liters. Later on today, we're going to learn what I consider a very convenient way to do conversions. But before we learn that, I want to see how your mind currently works to do a conversion like this. So we have a dry marker. .0 milliliters. We need to convert that to liters. How do you want to do this?
1 liter over 1,000 milliliters.
So you said 1 liter over
1,000 milliliters.
1,000 milliliters.
Because we want to get rid of the milliliters.
So you're essentially doing the method that we're going to do later on.
Oh.
No, that's fine.
Okay.
That's you just already know it.
Okay.
So mathematically, no matter how you do it, you're going to end up doing the same math here. But there's some different ways that you can think about it in your head. How else could you get from milliliters to liters? Yeah.
Could you move the decimal over?
You could just move the decimal. How many would you move it, and which way would you move it?
3, move it to the left.
You're going to move it to the left. How many?
2.
Why 3?
Because milliliter is thousands.
Yes. Milliliter is thousandths, which is 10 to the negative third. And so we're going to move it 3 places. So decimal place is now here. We have an empty spot here, so we have to put in that. The way my mind goes about a problem like this is I say there's 1,000 milliliters in a liter. And so I'm going to do something with 1,000. I'm either going to multiply by 1,000, or I'm going to divide by 1,000. But which one is it? And I go back and I think, well, which one is bigger? What is larger, a milliliter or a liter? A liter is larger. So if I go from milliliters to liters, is my number going to get larger or smaller? Smaller. Because the unit is larger, I need fewer of them. I don't need as many of them. It's like if I'm changing bills and I am going from $25 to $100 bills, I don't need nearly as many $100 bills to be worth as much as however many dollar bills I start with. So we're going from milliliters to liters. Because the unit is getting larger, our number is going to get smaller. So if I'm going to take 25 and make it smaller, do I need to multiply by 1,000 or divide by 1,000? Divide. If I divide by 1,000, it's going to get smaller. When you divide by 1,000, you end up moving the decimal place three spots. If we go back to what we have written here, mathematically we have 25 times 1 divided by 1,000, which is the same as 25 divided by 1,000. So no matter how we did it, we did the same math. It was just how we went about doing it. The second one we have up here is 25 milliliters to quarts. And this time they give us a conversion factor. They say 1 liter is equal to 1.057 quarts. You can do it the way where you start with 25, and then you multiply by your conversion factor. But we'll get to that. Using the more logical way. How would you convert from milliliters to quarts? We know 1 liter is 1.057 quarts. So really the only thing we have to figure out is, do we take 25 and multiply it by 1.057, or do we divide by 1.057? In order to figure that out, we have to decide which is larger, a liter or a quart.
A quart.
Why a quart?
No, yeah, a quart is larger.
How many
than
say a
liter.
quart?
There's 4 liters in a quart.
How many say liters? Okay. So this says 1 liter is 1.057 quarts. You need more than 1 quart in order to equal 1 liter. Now,
Oh.
since I've said that, which one is larger, the liter or the quart?
The liter.
The liter. Because you need more than one of these to equal that. Looking at it just in terms of numbers with no logic, the one that has the larger number is the smaller unit. So because that has the larger number, that's the smaller unit. Okay? So if I go from milliliters to quarts, I need to go to liters first. Okay? Some of these conversions are not going to be one step. Some are going to be 2 or more steps. Our conversion factor is only liters to quarts. We're starting with milliliters. So where do you want to go from milliliters? What do you want to do as our first step?
Go from milliliters to liters.
Go from milliliters to liters. That's what we did here, right? We already did milliliters to liters. And we know that is 0.025 25 milliliters is 0.025 liters. Now we can convert it to quarts. Do you want to multiply by 1.057 or do you want to divide? Where we said a liter is larger than a quart. So when we go from liters to quarts, should this number get larger or smaller?
You're going to multiply.
It should get larger. Because we're going to a smaller unit, our number should get larger. And so, to make this number larger, do I need to multiply or divide by 1.057?
Multiply.
Multiply. If I take 0.025 times 1.057, you get 0.0264 quarts. Don't forget your unit. These conversions are pretty simple. If you can follow this logic, you can always use it. Okay? If you are completely lost right now, don't worry.
Why did you stop at 4? Because it's really 0.026425.
That might be, if it's not, the next slide is coming up. But
Okay.
there is a reason we stopped there.
Okay.
So if you don't understand why we just did what we did, don't worry. There's another method coming up that what I consider to be the idiot guide to conversions. Okay? You don't actually have to know what you're doing to get the right answer, which is always great, right? Okay. So we talked about mass. We talked about volume. Now we can talk about density. Density is just the ratio of mass to volume. The equation for density is D equals mass over volume. It's dmv, but don't trick yourself up and remember it as dmv. That's wrong. This one is right. You're going to do this a whole bunch of times. That's going to get stuck in your head. But this is an equation that is not on the cheat sheet you will have. Okay? Most equations we use will be on that cheat sheet. Density is not one of them. Luckily, it's a pretty easy one. D equals M over V. For solids, and solids and liquids, the units are normally grams per milliliter. Okay? For gases, we use grams per liter. Gases, because the molecules are so far spread out, there's not much mass there. You know that gases don't weigh very much. And so in order to get a mass that's actually a number that you can work with, you need a lot of a gas. And so you normally use liters instead of milliliters. On the right there's a graduated cylinder with a bunch of different liquids in it. They separated based on their density. Which one is the most dense?
The brown.
The brown one, the one at the bottom. So then which one is the least dense?
The one on the top.
The one on the top. That looks like vegetable oil. Why is the most dense one on the bottom and the least dense one on the top?
Because
They sunk. Dense things sink. Things that are more dense go to the bottom. Things that are the least dense go to the top. A little test-taking trick. If you see something like this, and the question says which one is the most dense, and you have not a clue in the world, pick either the bottom one or the top one. Don't pick one of the ones in the middle. That one's never going to be right. If you pick the top or the bottom, because it says the most dense, you at least got a 50-50 chance. Dense things go to the bottom, least dense things go to the top. Just to give you an idea of what some of these density numbers look like, water here is 1 gram per milliliter.
that mixture would have been heterogeneous, right?
Yes.
Okay.
The heterogeneous mixture. So water is 1 gram per milliliter. And that's actually not a coincidence. They defined 1 gram as being the mass of 1 milliliter of water. That's where the gram unit came from. So density of water is 1. And these metals are generally above 1. Oil is slightly less than 1, which is why oil floats. Gases have very, very, very low densities. And then ice floats. Ice is actually pretty much the same as cooking oil. In general, gases are the least dense, solids are the most dense. Ice is actually an oddball. Ice is one case where the solid is less dense than the liquid. I think we'll talk more about why that is in another lecture, but you don't have to worry about that at this point. Just in general, solids are the most dense, gases are the least dense. So here we have our cube again. It says if the mass of the cube is 11.2 grams, what is the density? And the density equation is written out there for us. It says density equals mass over volume. In a problem like this, where you have an equation, the question has to give you every variable except one. In this equation, there are 3 variables. We have density, mass, and volume. Of those 3 variables, which one are we trying to solve for in this problem? Density. So that means we have to be given mass and volume. So we have density equals mass over volume. What is the mass?
11.2 grams.
11.2 grams. What is the volume?
8 centimeters cubed.
8 centimeters cubed. It's not specifically given to us. It's not written out in words, but this is that cube where they said the one side was 2. So 2 times 2 times 2 for length times width times height gives you 8. So we get 8 cubic centimeters. So you go 11.2 divided by 8, and you get 1.4 grams per cubic centimeter. And you can get that unit from a couple different ways. The one, if you wanted to take kind of a shot in the dark, but it's probably a good shot in the dark, because it's a solid, it's probably grams per cubic centimeter. But where that actually came from is grams divided by cubic centimeters. The unit part here is transferred over there.
Oh.
So if you had used milliliters here, instead of centimeters, it'd be grams per milliliter. If you had converted this to liters or to cubic meters, that just goes there. It doesn't really matter. Grams per cubic centimeter is the most common unit, but it's not the right unit. As long as your number is mathematically correct going with your unit, you're right. And so if you want to give this to me in kilograms per liter, I'm not going to be happy because I have to calculate whether you're right or wrong. But if you are right, you'll get it correct, okay? I want you to get the correct answer, not necessarily what I have written on my answer key. So we already talked about that. Here's a person floating in the deep sea, in the Dead Sea. Which is more dense, the person or the water?
The water.
The water. You look at that and you probably think the person floats, right? The person is floating. But when you really get down into the physics of it, it's really more the water sinks. The things sink because of more gravity. And so the water has stronger gravitational pull, so the water ends up on the bottom. But you're able to look at this and you can tell because the guy is floating, he is less dense than the water. So the water is more dense, the guy is less dense. Do you know why there's a picture of a person floating in the Dead Sea here? Why is it the Dead Sea? Yeah.
Isn't it in the Dead Sea, it's too much salt or something? So, yeah.
The Dead Sea is very, very, very high concentration of salt. and we'll learn months from now, but the more salt you dissolve in water,
Does that make it more dense?
it makes it more dense. And so the Dead Sea has even more salt than the ocean. So, has anyone ever noticed a difference swimming in fresh water versus swimming in the ocean? What is the difference?
It's a lot faster, it's a lot harder to stay afloat.
In which one?
Like if you swim in the springs,
Right.
it's pure fresh, it's very hard to stay afloat.
Right. The fresh water is low density compared to the others. It's much closer to us. We are mostly water. And so our density is very close to the density of water. And so if you get in fresh water, the densities aren't very different. And so it's harder to float. When you go into the ocean, it's easier to float. Unfortunately, if you're like me, you realize that fat floats. And so you float in fresh water just as well as you float in salt water, or as you would float in the Dead Sea if you were ever there. Okay? But if you are a lean swimmer, you might be able to notice something like this. Here we have two cubes. And I always have to qualify this as saying, believe it or not, these two cubes are the same size.
But they're not the same weight.
They're, right. To me, there's an optical illusion. To me, it looks like the gold one is much bigger than the silver one. Do you see that? No? Some people do, some people don't. It's like, what color is the dress? To me, this one visually looks much bigger than that one. But it's not.
The white background.
Right, it's just an optical illusion. Really, the gold one is the same size as the aluminum one. Okay, we're going to work on that assumption. They are the same size. It says the cube of gold has a greater mass. If gold one has greater mass, and they're both the same size, which one is more dense?
The gold.
The gold. Why? Right. You have more mass in the same volume. That's kind of a visual way of thinking about it. If we go back to the equation, D equals M over V. It says the volume is the same for both of them. If V is the same for both of them, the number that determines your density is your mass. If that M goes up, which direction does D go? Up. Things on the top of the fraction go the same direction as your answer. As mass goes up, density goes up. As mass goes down, density goes down. So because gold has the higher M, it has the higher D. Now, in this picture, the gold and the aluminum are definitely not the same size. In this picture, the gold and the aluminum balls have the same mass. If they have the same mass, which one has the greater density?
Neither, they're equal. Right?
Yeah.
Oh, no, no,
So, mass is the same, right? So M is not going to determine our D. Our D comes from our V. As that V goes up, which direction does D go?
Down.
Down. Because the V is on the bottom of the fraction, as the V goes up, that means you're dividing by a larger and larger number. If you divide by 1,000, your answer is going to be smaller than if you divide by 10. So as the V goes up, D goes down. So because aluminum has a larger V, it will have a smaller D. Gold has a smaller V, so the larger D. Just remember, density goes the same direction as mass. It goes the opposite direction of volume. This is water with regular Coke and Diet Coke. You can tell by looking at that picture that regular Coke is more dense. Why?
Sugar.
What about the sugar?
Sugar weighs more than, I guess, saccharin.
Saccharin is so much sweeter than regular sugar.
Oh, it requires less.
It requires less. It's like when you add more salt to water, it gets more dense. Saccharin is very, very sweet. If you open a pack of Sweet and Low, there's not much in there, right? You've seen a packet of the Sweet and Low versus the packet of sugar. Actually, most of what's in that package of Sweet and Low isn't even Sweet and Low. It's just filler. The amount of Sweet and Low needed is so small that people would open it and think there's nothing in here, I want my money back. So we put filler in there to go with it. Sweet and Low is very, very sweet until there's hardly any of it in Diet Coke at all. And so when you add a whole bunch of sugar to the regular Coke to get it to be as sweet, it's now really dense. So if you go to a cooler and the ice is mostly melted and you want regular Coke, you're going to have to reach down in that ice water to get your Coke. If you want Diet Coke, you can kind of pick it up off the top and try to keep your hand dry. So we said that ice floats, and that was kind of an exception. That normally, as you go from gas to liquid to solid, you get more dense. But you know, ice floats. This is what normally happens when you go gas to liquid to solid. The molecules get closer and then closer together. But ice makes this really fancy crystal lattice when it goes from a liquid to a solid. And so actually, when it goes from liquid to solid, the molecules actually have to pull apart a little bit in order to get this empty space in there. So that's why when you go from liquid water to solid water, ice, it gets less dense. The molecules actually pull apart from each other. Yeah.
It's up that space.
It's empty space. It is complete vacuum. I mean, it's the same thing that's between gas molecules here. It's kind of, at least for me, it's kind of hard to fathom that there's all this complete void. It's like mind-blowing stuff.
Is that why when you put a water bottle in the freezer, it expands and can grab the water bottle?
Right.
Okay.
Because you got the water in there and it's full, and when it freezes, it needs the space. And so it's going to expand, and either when it goes to expand, either the bottle itself is going to be strong enough to say, no, you can't expand, or the water is going to say, forget you, I'm going to expand, and all of a sudden it blows up in the freezer. Okay, moving on to temperature. Temperature is, at least for this week, we're going to say temperature is a measure of how hot or cold something is relative to a standard. Our scales for temperature always started somewhere, okay? We measure temperature with a thermometer. If you want to sound fancy, call it a thermometer. We, in science, use Celsius and Kelvins. We never, ever, ever use Fahrenheit, okay? In most cases, we're going to use Kelvins. In some cases, you're okay to use Celsius. These conversion factors are on your cheat sheet. You do not have to memorize how to go between the different units for temperature. But you need to be comfortable doing it, because it's probably going to be on the quiz next week, and it will certainly be on the first exam, and it will certainly be on the final exam. So you just need to be comfortable using these equations that are on here.
So if it's on a quiz and we don't have that sheet,
The only quiz you won't have the sheet for is today's.
okay.
And so, because today's quiz has no numbers involved, after today you will always have them for every quiz, for every exam, and for the final exam. So, when we look at this, let's start with this one. This says Kelvin equals Celsius plus 273.15. To go from Celsius to Kelvin, all you have to do is add 273.15. And that means going the opposite direction. To go from Kelvin to Celsius, you subtract it back off. So Kelvin minus 273.15 equals Celsius. The Fahrenheit to Celsius conversions are kind of wacky. I never remember them. But once you do this a couple of times, you'll remember the number 273.15 and you'll be good. Either way though, it is on there. So these are our three temperature scales. We said that temperature is based off a reference. So let's start with Celsius here in the middle. Ice melts and the freezing point of water is 0, boiling point of water is 100. That is where those numbers came from. Somebody said this temperature is where water freezes, I'm going to make that a 0. This is where water boils, I'm going to make that 100. It was completely out of the blue. They made the scale up based on that. They could have called that negative 70 and that 5 billion. It would have made it really confusing, but they could have given it any number they wanted. But this makes Celsius really easy because water freezes at 0, boils at 100. Okay? Room temperature is, everybody calls it 25. In all science literature you read, somebody says 25 degrees is room temperature. But in reality, room temperature is really more about 21 or 22. Then we go over to Kelvin here. Looking at this, it says water boils at 373.15. Room temperature is 298.15, and the freezing point of water is 273.15. Where did those numbers come from? There has to be some reference, some starting point. Where did those numbers come from?
The lowest possible temperature being 0?
Yes. Have you ever heard of absolute zero? Absolute zero is the complete absence of heat. It is as cold can possibly be. That's what Kelvin is. 0 Kelvin is 0 heat. And then you just go up from there. You can't have negative Kelvin. So 0 is nothing, and then you go up. And it just so happens to be that water freezes at 273.15. And it so happens to be that water boils at 373.15. Okay? These numbers are not numbers you need to memorize. I have no idea. I remember this freezes at 0, boils at 100, and then I know how to convert between the two. Add 273.15. Now we get to Fahrenheit. We've got liquid water boils at 212. Room temperature is 77. And ice melts at 32. And the lowest possible temperature is negative 460. None of them make sense. America, right? Where did that come from? It makes no sense. Do you see anything up here? Does anything jump out there as being logical? 0 and 100. Celsius. What is body temperature?
98.6 degrees.
98.6
Degrees Fahrenheit.
Now imagine you were measuring body temperature hundreds of years ago. And your thermometer wasn't nearly as good as our thermometers are today. What do you think 98.6 might have looked like?
Well, if you flip that thermometer sideways.
Well, what is 98.6 very close to?
100.
100. Dr. Fahrenheit, or whoever he was, said body temperature is 100. But then we realized later on, oops, it's not actually 100, it's 98.6. So he said body temperature is 100, and then these other numbers fell wherever they fell. But now we know body temperature is actually 98.6, so none of the numbers make sense at all. But it's what we work with. Okay. Moving on to temperature. Everybody comfortable with temperature? Okay. Now we've got precision and accuracy. These are two words that people outside of this room use occasionally. But outside of this room, they probably use them interchangeably, which is incorrect. Precision and accuracy are two different things. Precision is how repeatable your measurement is. If you have a series of measurements and they're close in value, they are precise. It doesn't matter how close they are to the actual number. So I am just under 6 foot, okay? So if we measure my height, and you say that I am 1 foot, second time you say 1 foot, third time you say 2 foot, fourth time you say 1 foot. Is that precise?
No. Well.
It actually is.
Okay.
Precise has nothing to do with how good the measurements are. It is only how close together they are, how repeatable they are. So I measured 4 times, I got the same number 3 times, and the other one was only 1 off. They're close together. They are precise. Accuracy is how close the measurements are to the actual number. These measurements are not accurate. They are precise because they're close together, but they are not accurate. When we talk about accuracy with a set of measurements, we actually talk about the average measurement. And so you're not saying that this one is accurate and that one's not. You take the whole group. You calculate the average of those 4 numbers. And that's going to be 1.2-ish, somewhere in there. 1.2. Well, yeah, of course. 1.25. So the average is 1.25. So you compare 1.25 to the actual number. The actual number is 6. Is that accurate? No. Because the 4 numbers on their own are close to each other, it's precise, but the average measurement is nowhere near what it's supposed to be, so it is not accurate. So this is how we were looking at it with numbers. Okay? You can also think of it as a target. So here we have our target. We're shooting for the bullseye in the middle. And we have our shots. Looking at that, first would you say is precise? Are those shots precise?
No.
No. For precision, something like this, you're looking at how tight the group is. Are the shots close to each other? Regardless of where they are they close to each other? They are definitely not. And so that is not precise. Then you have to answer, is it accurate? In your mind, you have to kind of figure out, what is the average spot there? Where do those shots average out to be? What is the middle of that group?
1.8.
To me, I say, well, there are more dots on the left than there are on the right. Did you see that? And so the average is going to be somewhere to the left of the middle, and there are slightly more on the bottom than there are on the top. And so to the left and down, somewhere in here, it's eyeball, okay? If that is the average, would you call that accurate?
No.
It's a little subjective, because you could say, well, how close do you have to be in the middle to be accurate? But I think most people would agree that if you're in the blue here, not in the red, that's not accurate. And so we're going to say that is not accurate and not precise. What about that one? Precise. They're very close together. Is it accurate?
No.
So that's not accurate, but precise. How about that one? Is it precise? Yes. Is it accurate?
Yeah.
Yes. They're all in the bullseye. So that is accurate and precise. What about that one? Is it precise?
No.
No, it's not precise. Is it accurate? How many say yes? How many say no? So they're spread way out. I mean, that's not something to be proud of. But if you figure out where the average is. They're pretty much spread equally around the center. I mean, they're kind of a shift to the right maybe a little bit. But I would say the average is probably right about there. That's pretty close to the middle. So I personally would say that the average there is accurate. I would call that accurate, but not precise. Because it's subjective, if you want to make the case that, well, that's not good enough, the average is here, that's not right in the middle, you can make that case. But on a quiz or an exam or something, I'm not going to pick that one. I'm going to pick probably that one, and that one, where it's obvious whether it's accurate or not. Okay. Go back to our conversions. You're going to do these conversions a lot this semester. So we need to convert 12 grams to milligrams. First of all, what is larger, a gram or a milligram? A gram is larger. So when you go from grams to milligrams, you are going to the smaller unit. If you're going to the smaller unit, will your number get larger or smaller? Larger. If you go to a smaller unit, our number needs to get larger. How many milligrams are in a gram? 1,000. Milli means thousandth, thousand or thousandth. So we've got that number. We know we want a number to go up, and we're going to use 1,000 to do it. So do I take my 12 grams and multiply by 1,000 or divide by 1,000? Multiply. So you take 12 grams times 1,000, it's going to be 12,000 milligrams. That's that thing at the end there, scientific notation, that's coming up in a few slides. On the bottom, we've got 12 grams to ounces. What is larger, based on the conversion factor we're given, an ounce or a gram? Which one has the larger number? Grams is the larger number. That means it's a smaller unit. So ounces is the larger unit. So when we go from grams to ounces, is our number going to get smaller or larger? It's going to get smaller. We're going to the larger unit. We're going from grams to ounces. Ounces are bigger, so our number will get smaller. So we take our 12, and we have to make it smaller. To make it smaller, do we multiply by 28.34 or divide? Divide. Obviously, if you multiply by 28, your number is going to get larger. So you divide by 28.4, and you get 0.423. Now, she asked before, why is 0.423? If you put that in your calculator, it's probably going to give you 0.4234. Why did you not put all the numbers? And why did you not round it at 0.42? Anybody know? Yeah. Significant figures. Does that make anybody cry?
Yes.
Yes. Sig fig. We call significant figures sig figs. Yes, things like this actually happen. And yes, organic chemistry can take an entire week of actually working, not just procrastinating, to write a lab report. So significant figures are the bane of human existence. Okay? Nobody likes them. Don't even pretend that I like them, because I don't. Okay? I'm on your side. Significant figures. Okay. They tell us which numbers we are confident in a measurement. Where these come from is when you take a measurement in a lab, and then you tell me that measurement, you need to have some way of telling me how confident you are in that number that you gave me. Okay? If you write a number, let's say 29.5, the last number that you write is always sort of uncertain. So when you write 29.5, when you tell me that is your measurement, you're telling me you think that last number is 5, but that's not set in stone. But you are confident in the 2 and the 9. You know those are right. It's the last one that you're not sure of. So then you give me that measurement. I take my own measurement on something else, and then let's say we have to do some math, and we combine your measurement with mine. And then we have to figure out, well, how confident are we in our answer? I mean, we took 2 measurements. We had different confidence levels in the 2. How confident are we in your answer? So we have ways to figure out how many sig figs need to be in your answer based off what you put in. Okay? And the first thing you have to learn is how to figure out, when you look at a number, which digits are significant. And so it says significant figures. By figures, we mean digits. A digit is a number as a part of a larger number. So there are some rules here. Anything that's not a 0 is significant. Okay? Really, the confusion comes in with the zeros. If it is not a 0, it is significant. Always. If you have a 0 that falls between 2 significant digits, meaning a 0 between 2 non-zeros, it is always significant. So here we have 405. That 4 is significant, the 5 is significant. Because the 0 is between them, it is significant. And so we say that number has 3 sig figs. 1, 2, 3. It doesn't matter that this decimal point is there. That 0 is still significant because it is between the 4 and the 5. So 40.5 has 3 sig figs. If you have zeros in front of a decimal, we call them leading zeros. They're in front of your number. If they're to the left of every single non-zero, these zeros are to the left of where the good stuff starts, down here. They're leading zeros. They are not significant. They are never, ever significant. Then we have trailing zeros. Trailing zeros are zeros at the end. Okay? Trailing zeros at the end are significant if there is a decimal point written in the number somewhere. It doesn't matter where. If you have a decimal point written and you have trailing zeros, the trailing zeros are significant. If you have trailing zeros and there is no decimal point, they are not significant. This is the one that really trips people up. Because sometimes they are, sometimes they aren't. These never are. That one always is. That one always is. But this one's a what if. So, we've got this number. How many sig figs are in 26? 2. We have 2 digits. Neither of them are zeros. That was easy. We have 2. How about in that one? 7. We got 1, 2, 3, 4, 5, 6, 7. Why do you say those zeros are significant? There's a decimal and they are trailing. There's a decimal and they are trailing, and so they are significant. What about this one? 4. Why are these zeros not significant? Because they're leading. Leading zeros are never significant whether there's a decimal point or not. It doesn't matter. Leading zeros are just placeholders. They just hold the place so that you can put your actual number down where it belongs. This is scientific notation. These 2 are scientific notation. I think that's the next thing coming up. If you're looking at sig figs in scientific notation, you completely ignore this times 10 to the whatever. You just look at the first number. So how many sig figs are in that? 1. And how many sig figs are in that one? Well, the big question is that 0 significant? Is it? Yes. It's significant because it's between non-zeros, which means everything is significant, so it's just counting. 1, 2, 3, 4, 5, 6, 7, 8. Everyone feel confident in counting sig figs. Oh. That's how you count them. Where people struggle, then, is remembering to follow through with them. If you use measurements, and you use numbers in a mathematical calculation, you need to apply rules to your answer to figure out how many sig figs your answer should be. Multiplication and division is easy. You look at the numbers that you put in, you count how many sig figs were in all the numbers you put in, and the smallest number that you put in, that's how many your answer has. So let's use this first one as an example. How many sig figs does this number have? 3. How many does that one have? 2. So you've got 3 and 2. Your answer has however many was the smallest number that you put in. What's the smallest number we put in? 2. So our answer can only have 2 sig figs. And so you round it. You have to round this number to 2 sig figs. So you say, if I draw a line here, I'm going to have 8 point something, which has 2 sig figs. So I need to round from the right of that line to the left of the line. And you round it just like you would round any other number. So 8.853 rounds up to 8.9. Okay? The rounding rules are the same as you've always done. So we've got 6 divided by 3. How many sig figs should our answer have? 2. Why 2? Smallest number has 2. That has 2. That has 3. What is 6 divided by 3? 2. So how do you write 2 with 2 sig figs? 2.0. You put 2.0, 6.0 divided by 3.00 in your calculator. It's just going to tell you 2. That only has 1 sig fig. You have to be the human and add the second sig fig. I can add 0.0. You know that 2 and 2.0 are the same number, right? 2 and 2.0 are the same. But 2.0 has 2 sig figs where 2 only has 1. What about this? How many sig figs is our answer going to have here? 1. What happens when you put that in your calculator? You get 4.48. Is it 9? Is it 9? 4.49. 38, and a bunch of stuff. How many sig figs should our answer have?
1. And you're
1.
rounding down.
And so we end up rounding down because that is going to be our 1 sig fig. So we round it down. What is our actual answer? 4. So 4.4 times 1.123456789 is 4. Nothing happened. Nothing to see here, right? Sometimes sig figs do weird things like that. It's a matter of, if these were measurements, this means yes, you are very, very confident in that number. But that doesn't matter because you have no idea whether you're right on that. That's just kind of a ballpark number, basically. And so there's no use in saying it's 4.4938 when you had no idea how accurate your 4 actually was. What about 5 times 2? You should
But
have
the
2 sig figs.
trailing zeros are irrelevant, right?
Trailing zeros? Trailing zeros are significant if they're the decimal place. So that has 2, that has 2. So how many should your answer have? 2. What is 5 times 2? 10. How do I write 10 with 2 sig figs? Add a decimal. You mean like that? No. How many sig figs does that have? 3. And so what you end up doing is you just add a decimal.
Why do you have decimal? Oh, 0.
Because when you add that decimal, that trailing 0 is now significant. And so now that 0 is significant, we have 2. If I add that one to make it look right, it's actually wrong. That has 3 sig figs. And so you can have a number that just ends with a decimal. Nothing after. Let's take our break now, and we'll start a little bit after 7:30 on that clock. That's 10 minutes.
bring one of my sofa.
They're more comfortable than the other systems. And then you have classes all over the shows.
Are there left-handed versions? Because there at least were a few of the old desks that were left-handed.
I don't think it matters, because there isn't like a, if you have these on the.
Are there any left-handed people in here?
Yeah, it goes all the way to the
Whoa,
other side.
wait a minute. There's that many left-handed people in here? Well, they all raised their left hand, so I guess that's kind of a odd thing.
The desk actually doesn't, like, it doesn't bother you.
It doesn't bother you?
Not like the other one did. It's the thing.
Yeah, because the other ones have like, they connect on the side and then you get them on the side.
Yeah.
But these desks, they move over. So you can kind of adjust it.
Apparently, they've now asked that when we leave, this isn't us, it wouldn't say that department. They want desks put back in some semblance of rows. Because you saw what they look like, a picture looked like this when you walked in.
Oh,
Which
yeah.
is not what they want. And so when you leave, you can kind of make some semblance of rows, it would be appreciated.
So if we group them all together, that would be good.
Everybody, looks like everybody's back.
What would that be accurate?
They're very precise, but they're not where they're supposed to be. So it's not accurate. And I don't really feel like emailing my chair and saying, but they were precise in what they did. They just weren't accurate to what they wanted. Okay. So this was multiplication and division. This is the easy one. Okay. And fortunately, this is the one you're going to be doing the most of. Okay. Most math we do in here is multiplication and division. Believe it or not, it's addition and subtraction that's to bang your head against the wall annoying. Okay? You can't do this in a calculator. You actually have to do it longhand like you learned in second grade. Okay? You can't just look at how many sig figs what you started with and then that's how many you end with. Okay? You have to figure out where the decimal places end. It actually doesn't have to do with the sig figs that go in. It's the decimal places that go in that determine how many decimal places you get out. And so it's possible that you could start with two numbers that have one sig fig and three sig figs and get an answer that has two. Okay? Sig figs completely go out the window. It doesn't matter how many were in when you started, and you get your answer. What you need to do is you need to line the numbers up with the decimal places in a line, the decimal points in a line. So we're adding these three numbers. You line them up and so that the decimal points are in line with each other. And then let the numbers fall where they're going to fall. We then look on the right-hand side and we say, at what point does the first number, the first meaning we go from left to right, where does the number end? What's the end of the first number that you run into? So this one ends down here, this one ends here, this one ends here. As we go from left to right, we run into the end of that number. When we run into the end of a number, we draw a vertical line. We draw the vertical line, then we do our math just like we would always do it. So we get a number, and then we round from the right side of the line to the left. So we line the three numbers up, decimal places in the same spot. Decimal place ends up in the same spot in our answer also. You do the math just like you were completely ignoring sig figs. You put these in your calculator, you do it longhand, you get 4,690.526. Okay? But we drew this line here. And on the left of the line is one decimal place, on the right is 2. Because this number didn't have a second or third decimal place, our answer can't have a second or third decimal place. And so we drew this line here, and so you have the line, you have your answer, you round from the right to the left. Does 226 round up or down? Down. And so it just basically goes away, and our answer is 4690.5. Yeah.
How did you decide where to draw the line?
We start on the left, and we move right. So if we start on the left, we got 4 here. Neither of these have a number. And so we haven't reached the end of a number yet. So we move over. Now we've got here, and here, and then here, and then here, and then we get to here. These numbers are still going, but this one ended.
So you draw it after whichever one ends.
Ends first, right? If
It's
you-
not one space after the decimal?
No. In this case, it is.
Oh, but that changes?
Right.
So if it had, say, the bottom number had a 2 after it, you would
Yes.
draw it after,
So
technically
if
after
this
that.
one had a 2 here, then the line would be here. Because these two ended here, even though that one was still going. If you wanted to put it into words, and this is going to be completely confusing when I say it, it would be draw the line after the rightmost final digit. You have no idea what I just said. But that completely explains that. Okay? So that does make sense?
Yeah.
Okay.
Not to me, but it's wherever wherever it trails off, and you now have a blank space.
You find the first number, the number that ends the soonest,
Uh-huh.
and draw a line after that, and then anything that falls on the right
Okay.
is rounded over.
All right.
So, okay, I'm wrong.
Okay,
So
let's do
what
it.
if that wasn't a 9, it was like a 6 or something, would you still keep going?
You would draw the line
You see,
after
if
the
that
6.
was- If that was a 6 instead of a 9, that would have no impact on mine.
Oh.
Let's do a simpler one. So that one has 3. Let's do a simpler one with just a couple. You've got 2 plus 3.1.
Wait, zeros count, like if the 9 was a 0?
Yes. In this case, because we don't care about how many sig figs we started with, all we care about is digits.
So you're gonna draw the line after the 2?
Right. So this one ends here, this one ends here, so you draw after where the first one ends. That one ends here, there's nothing after that 2.
So the answer is just 5.
Right. So when you do the math, you're gonna get 5.1, but because the 1 is on the right side of the line, it has to go away. And so you round it. And 1 rounds down, and so your answer is just 5.
You don't include the decimal?
It doesn't matter.
It doesn't matter? Okay.
So if let's say we have 1.0, 12.81, and 5.591. I'm going to add them all together. Where am I going to draw my line?
After the 0.
This one ends here, this one ends here, this one ends here. You draw it after the first one ends. When I mean first, I mean from left to right, not just because top one.
Even if it's a 0.
Even if it's a 0. So I'm going to draw my line here.
Got it.
And so I do the math, I get 1, 0, 8, 9, 14, 5, 6, 7, 8, 9, 1. Decimal point is there. So what is my actual answer? 19.4, because this rounds down.
So what if I run it up?
It would be wrong.
Because of the line.
Yeah. This is a 0, 1. So 0 rounds down.
Right, had that been 6.
If this was 6?
Yeah.
Yeah. So if this
0.5.
was, that'd be a 6. 6 more. So that would be a 7. That was a 7, but that was a 6. Then that would round up to 19.5.
19.5 would be your answer?
19.5 would be the answer. So, those are sig fig rules. Okay? They come from the kings and queens of chemistry from centuries ago. No one likes them, but we gotta deal with them, okay? Our pact is that if any of us ever become king or queen of chemistry, we get rid of them, okay? But because that is not the case, we can't get rid of them yet. For next week's quiz, for the first exam, where I am actually testing you specifically on sig figs, I am going to be watching them like a hawk, okay? You have to have them. After that, you should have sig figs. You should figure out sig fig in every single mathematical problem you do in this course from here on out. But I will get much more lenient on them after this quiz in this exam where I am testing you specifically on it. If we do a reaction problem and I ask you to calculate how much product you can make and you don't do sig figs, a month from now, I'm probably not going to mark it wrong. Okay? I used to, it just was not. I mean, your students don't do it because they are rebellious or something. They just forget. And so I kept marking off and marking off and marking off and marking off. And I don't take many points away for it. So it was basically a waste of everyone's time. So if the question is about sig figs, you gotta do it. After that, I suggest you do them because if you go and take another science class, that professor may be a stickler on them. Okay? And when I took all kinds of college classes in chemistry, and we had to do it every single time. So here we've got 587 point something 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 plus something and minus something. In this case, you can't do 587.362
708.
708 minus
4.36.
4.36 plus.
No, minus. It's plus 4.36. Minus 9289.
Let's go back. 329. 329. 829. 829. I don't know about you, but when I was in second grade, I didn't learn how to do it longhand with a plus and a minus together. And so if you want to do it this, you're either going to have to do the plus part, get an answer, then subtract the minus part, or what you can do is do this in your calculator. Can somebody do this in your calculator for me? And then we're going to write our answer down here relative to we're going to keep decimal place in the same spot, and we're going to write our number off of that. So if somebody has an answer, let me know.
Negative.
Okay. So you got your answer?
Mm-hmm.
So we're going to start at the decimal point
Okay.
and go to the right. And
Okay.
read off the digits for me.
5562.
That's 5, 5, 6, 2.
2. That's it.
That's it. And then starting at the decimal place and going to the left.
928. Oh, sorry. 133.
1, 3, 3,
8 2.
8,
9.
2, 9. That?
Yeah.
And the whole thing's negative.
Yeah.
Okay. So we did that. We've got our answer. Now we have to go back and draw our line. Where do we draw our line?
After the 6 in the 4.36.
That one ends the soonest. So I draw the line there. So what happens to this 6, 2?
Goes away.
It rounds up.
Oh.
And so that will become 0.56.
6.
Where things get even more complicated is if you have a problem that has both multiplication and division and addition and subtraction in it. You have to do step by step by step, following sig figs as you go. But I will not give you a problem like that on a quiz or something. Okay? Me personally, if I see a question like that, I get lazy. I just follow the multiplication division. The smallest one is what you get. If you don't like it, oh well. So I'm not going to make you do that.
So it's not on an exam?
No. If you have a question like this, where I'm looking to see if you know the rules, it's going to be addition, subtraction, or multiplication, division. And it's not going to be one of these plus and minuses together. It would not be something like that. It would be a straightforward rule. Okay, now I've got our scientific notation. Scientific notation is a way of writing very large and very small numbers in a manageable way. Okay? Scientific notation is this generic form. We have C. C is just going to be a number times 10 to the n. C is a number from 1 to 10. It cannot be less than 1. It can't be 0.5. It has to be between 1 and 10. And it cannot be above 10. It can't be 10.1. N is an exponent, and it's a positive or negative integer. What is an integer?
1, 2, 3, 4, 5.
Yeah.
Yeah, they're whole
number.
numbers. You can't have 10 to the 1.1. You can have 10 to the 1, 2, 3, 10 to the negative 1, negative 2, negative 3. You can have 10 to the 0. They have to be a whole number. If we're going from normal number, what we call expanded notation or non-scientific notation, when we want to go to scientific notation, we move the decimal point to the right of the first non-zero digit. So if I have 820, what do you think is the first non-zero digit?
2.
8. Because we start from the left, we have an 8. That's non-zero, so we move it to the right of the first non-zero digit. Basically, you want to put it so that you have one digit to the left of the decimal point. That's another way of looking at it. You put it so that you have one digit to the left. And then we count. How many places did we move that decimal place? Where did the decimal place start? It started here. We didn't write it, because if we wrote it there, then that would change whether the zero was significant. But mathematically, the decimal place was there. It was 820. Decimal point place was there. So how many places did we move it?
2.
2. We moved it 1, 2. So we get 8.20 times 10 to the 2. If you move the decimal place to the left, it's a positive number. If you move it to the right, it's a negative number. So if I have 0.035, where am I going to move the decimal place to? To the right of the 3. I'm going to move it to here. How many places did I move it? 2. I moved it 1, 2. So I have 3.5 times 10 to the what? Negative 2. $3,245. Which one am I going to move the decimal? Left. It is currently here. I'm going to move it 1, 2, 3 to the left. So what is that number in scientific notation? 3.245 times 10 to the third. We moved it 3, we moved it to the left, so it's positive 3. What about this one? Which way are we going to move the decimal, left or right? Right. And so what does that make it in scientific notation? 3.245 times 10 to the negative, right? Do that, okay? If it's up here, take your finger and go like this, okay? If it's on paper, take your pencil and do this. If you try to eyeball it, if you try to be brave and confident and cool and eyeball it, you're just going to mess it up, okay? If Albert Einstein was in this class, he would take his finger and go like that. Everybody does it, okay? Do it. So, 1, 2, 3, 4, 5, 6. 3.245 times 10 to the negative 6. What about this one? Move it to the left or right? Left. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3.245 times 10 to the positive 9. How about this one? Move it to the right. 1, 2, 3. You got 5.0607 times 10 to the negative 3rd. 88. What do we do with that? 8.8 times 10 to the 1. And how about that one? What do we do with that? Okay. It's already in the right place. So how many places do we have to move it? None. If you moved it none, 2.45, you moved it 0 places. Do you know what is any number raised to the power of 0? 1. You can multiply anything by 1, it doesn't matter, right? So we multiply 2.45 times 1 is 2.45. But if the question was demanding that you put it in scientific notation, that's not scientific notation, but that is. Different calculators do scientific notation slightly differently. Okay? Hopefully you have a scientific calculator by now. If you don't, hopefully you have one by the quiz next week. Okay? You can always do something like 5 times 10, and then there's probably a caret, 5 times 10 to the 3. That would be 5 times 10 to the 3rd. Okay? I suggest that you don't do this. For now, it'll be fine. But when you start doing math with these, your order of operation gets all crazy. Because if you have a problem that says 1 times 10 to the 8th divided by 5 times 10 to the 9th, what people like to do is they put in the calculator 1 times 10 to the 8th divided by 5 times 10 to the 9th.
Need parentheses.
Right. What this is going to do is divided by 5 times 10 to the 9th. And you're going to get a completely wrong answer. If you want to put it in your calculator like this, put parentheses. Okay? The way I suggest doing it, and the way I do it, is most calculators have a button specifically for this. It's either going to be EE or EXP. Okay? It may be a button that you have to hit second and then another button in order to get it. That means times 10 to the. And so if I wanted to do 5 times 10 to the 3rd, I would go 5 EE3. Some calculators, mine included, for some reason, when you hit the EE button, it actually only shows 1 E. But 5E3. When you do it like that, it knows that that is a package together. So you don't have to worry about parentheses. If you do this, make sure you're using the capital E. There's a lowercase e. That is something very, very different. Okay? That will not give you the answer you're looking for. If you want, you can show me a calculator and I'll help you find what you need to do.
I have a question.
Yes?
So when during this, I put 5E3, I just get 5,000, or is it supposed to show a
just put in 5E3 in your calculator and hit enter, it's going to take it out of scientific notation for you. It's going to say, what does 5E3 equal? That's 5,000. Okay? But if you did 1E8 divided by 5E9, it's going to give you a more complicated answer. It may or may not be in scientific notation depending how big it is. Graphing calculators will automatically put it in the scientific notation if it's a really big or a really small number. If it's something that they can show you the whole number and it's still a practical number, they're going to give it to you not in scientific notation. So in terms of answers on problems, if the problem does not specifically say it needs to be in scientific notation for an answer, I don't care whether it is or not. Okay? But if it specifically says it has to be, it has to be. If it doesn't say you can give it to me either in regular or scientific notation, I'll figure out whether you're right. We did a bunch of those. Scientific notation has some math rules that go with it also. If we multiply two numbers in scientific notation, we take the coefficients. The coefficients of the numbers, we multiply them together to get a number, to get another number. And then we take the exponents and add them together. So, if we take this, we get 4 times 1.5. So that's 4 times 1.5. And then we take the exponents, 6 and -3, and add them together. So what it ends up being is 4 times 1.5 is 6. 6 times 10 to the something. What is 6 plus -3? 6 plus -3 is 3. Plus -3 is the same as just minus 3. So it becomes 6 times 10 to the third. 6 is 4 times 1.5. 4 times 1.5 is 6. The 3 is 6 plus -3 is 3. When you divide, it's basically the same thing. You're going to take your coefficients and do the math for them. So you get 4 divided by 2 is 2. And then we take the first exponent, -2, and subtract the second one. So what is -2 minus 3? -5. So you end up with 2 times 10 to the -5. If you take scientific notation and you raise it to an exponent, so basically you end up with something like this. You take the exponent, you apply it to the coefficient. So you end up with 3 squared, which is 9. And then you multiply your exponent with the other exponent. So it's 4 times 2. So you get 9 with 3 times 3 squared. 3 squared is 9. And then 4 times 2 is 8. Yes?
And we have to put 9.0 because it's 3.0, right?
Right, because we started with 2 sig figs. That's the only number we started with, so sig figs just carry over. That had 2, so the answer has 2. Very good. Anything else? So, if we do this math, what do we do with the coefficients? We multiply them together. What is 6.78 times 5.55?
37.629. Would you round it? Because it's 629.
It's 629. So the calculator gives 629. What do we round it to? Do we round it?
Well,
How many sig figs should our answer have? 3. 6 point, that has 3, that has 3. So our answer should have 3. So how do we write that with 3 sig figs? 37.6. 0.29 rounds down. So that's the coefficient. Then we got 10 times 10 to the negative 1. We add the two together. 3 plus negative 4. 3 plus negative 4 is negative 1. What about the second one? We have 2.99 divided by 4.03. What is that? Did you divide it by?
Oh, sorry.
0.7419.
0.794.
No, 0.741935.
741935. We'll stop it.
Okay.
Then what do we do with our exponent?
Subtract.
Subtract what? Negative 9 minus negative 6. That's negative 3.
Negative 3.
9 minus negative 6 is basically negative 9. It's the same as negative 9 plus 6, which is equal to negative 3. So we've got that times 10 to the negative 3. Is that the correct answer? No. What's wrong with it? Sig figs. How many sig figs do we need? 3. So we've got 1, 2, 3. I'm going to round that.
Rounding up, right?
So it rounds up. We've got a 2. Is that the correct answer? It's actually not.
No.
What's wrong? Say again? 0 is not a sig fig, but it is something about that 0. Yeah. Yes. In order to be in scientific notation, decimal point has to be to the right of the first non-zero. So we're going to move the decimal place one spot to the right. What does that then do to that? It changes it. How much does it change it?
So it's to the negative 1.
It changes it by 1 because we moved it one spot.
Oh.
Does
so
it go
negative
up
2.
by 1 or down by 1?
Negative 2.
Be careful. Because it's negative, when you go down, the number actually goes from negative 3
Oh, to 4.
to negative 4. Be careful with your number line. Negative 4 is smaller than negative 3. Because that's something you know, you just have to be conscious that it's kind of catchy. You have to watch out for what you're doing. Yeah, actually, we should have. So we've got 37.6 times 10 to the negative 1. What should that have been? We need to move it over 1 here. So we get 3.76 times 10 to the what? We move to the left by 1, and so our exponent goes up by 1. 0.
So why are we moving the decimal?
Because if we went all the way back to the slide where it defines scientific notation, this number has to be between 1 and 10. It can't be less than 1, and it can't be more than 10. Yeah.
But if you were to put the whole equation into your calculator properly, it's going to tell you it's 7.41935 blah, 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 blah to the negative 4.
Yes.
So it's going to, if you know how to round it and where to stop.
Yes. If you want to do it in your calculator, it'll give it to you. The scientific notation will be correct. You
Yeah.
just have to know the sig figs.
Okay. Okay, because that's a whole lot easier.
Yeah, that's fine. And for the last one, we have raised to an exponent. We take the 4, 7 to the 4. What's 7 to the 4th power? Seven to the 4th power? 2401. Okay. And then what do we do here? multiplying together, 3 times 4 is 12. That is larger than 10, so we have to move the decimal place. We're going to move it 1, 2, 3. So now we have 2.401 times 10 to the what? 15. We moved it 3 to the left, so our exponent goes up by 3 to 15. Is this the correct answer? No. Why not?
Because it only has one number.
Sig figs. We started with this a 7, and so we can only have one sig fig with 2.
That's 2 times 10 to
2 times 10 to the 15. You just got to get through the sig figs for like the next quiz and then the first exam. The last thing we're going to talk about today is dimensional analysis. This is that conversion thing that I was talking about. It's idiot proof. Okay? And I'm not talking about you're the idiots and you're going to be using it. Okay? It just doesn't matter if you know what you're doing or not. You all know what you're doing, right? Everybody's going to nod their head. Everybody knows exactly what they're doing. So you are not idiots here. But when it's idiot proof, people who are not idiots can use it really, really well. So what dimensional analysis does is a roadmap. Okay? The units are going to tell you what to do. The numbers are just going to go along for the ride. If you're doing a dimensional analysis problem, the first thing you do is you look at what are we starting at? What is our starting point? And where am I trying to get to? And when I say that, I'm talking about units. What unit am I starting with in my conversion? And what units am I trying to get to for my answer? You then have conversion factors that you're just going to lay out one after another. They're going to take you from where you started to where you want to be.
You said that's just supposed to be easier.
I hope it should.
It actually is.
I'm hoping that once we get through it, and once it clicks, the units should help you here. So there are 2 ways of writing this out. Okay, there's the way that I learned, and the way I think makes more sense, and then there's the way that the book shows you. Okay, when we do dimensional analysis, generally, at least for today, both methods will be up here. Okay, I will do the grid method up here. In a couple of cases, I've put them on the slide, but I've also left the book's work in there so that you can see the other way if you want to do it. So the first example is convert 2 inches centimeters. And we're given the conversion factor 1 inch equals 2.54 centimeters. When you're doing this, figure out where you are starting, where you're trying to get to. What units are you starting with? Inches. And what units are we trying to get to?
Centimeters.
Centimeters. So I'm starting with inches. So I write inches. How many inches are we starting with? 2. So I write 2 inches. And I immediately draw boxes. Okay? The number that you start with always ends up in the top left corner. Always. Then we have this unit here. Whatever unit that is, it doesn't matter. Whatever it is, write it down there. What we're going to do is we're going to cancel units as we go. And you'll see what I mean by that. The inches are here. If we take inches, divide by inches, they go away. So we have inches and inches. When we have a number over another number, that's a conversion factor. The thing on top equals the thing on the bottom. So we have a conversion factor. 1 inch equals 2.54 centimeters. So I'm going to put 1 inch equals 2.54 centimeters. The unit that you want your answer to be in should be in the top right corner of your grid. In this case, we only needed to do one step. In other cases, you're going to have to do multiple steps. So you keep adding steps until you get your final unit in the top right corner. So in this case, you have inches and inches. And you have something on the top and the bottom, cross them out. Only unit that's left is centimeters. So your answer is going to be in centimeters. Now, to get the number, you take all the numbers on the top and you multiply them together. So you have 2 times 2.54, which is 5.08. And then you copy this horizontal line. Then you multiply all the numbers on the bottom and put it here. In this case, it's just a 1. You have 5.08 over 1. Take that number, divide it by that, equals 5.08 centimeters. Now we do our sig figs, there's only 1, and so the answer is 5 centimeters. I didn't think about what is larger, inches or centimeters. I didn't figure out, do I need to multiply or divide? The units told me. Because I had to have inches here, that means centimeters had to be on top. There was no other choice. 1 inch equals 2.54 centimeters. The numbers follow the units, you plug them in, and calculate your answer. So here is a longer multi-step one. We have to calculate how many inches are in 2 kilometers. In this problem, where are we starting?
2 kilometers.
2 kilometers. Can everybody look at that problem and see that we're starting our conversion with 2 kilometers? Okay, so we're starting with 2 kilometers. What are we trying to get to? What is the unit we're trying to get to?
Centimeters. Oh.
Inches.
Inches.
So we're going to do step after step after step until we have inches in the top right corner. If you had a direct conversion between kilometers and inches, you could do it in 1 step. But we don't have that. We have some other ones that we can use. So I started with 2 kilometers. I'm going to draw my box. That unit is here. That unit goes here. No questions about it. Just do it. So that kilometers is here. What conversion factor do we have that includes kilometers that you think might be helpful?
Meters.
1,000 meters equals 1 kilometer. So I can put 1 kilometer equals 1,000 meters. Do I have inches in my top right corner? No. So I'm not done. So I add another set of boxes.
And we keep going.
Meters is here, so it automatically goes there. No questions asked. Now, what conversion factor might be useful?
100 centimeters equals 1 meter.
100 centimeters equals 1 meter. So 1 meter equals 100 centimeters. Do I have inches in the top right corner? No.
No.
So I'm not done. So I draw another box. Centimeters are here, so centimeters go here. Now what conversion factor do I want?
1 inch equals 2.54 centimeters.
1 inch equals 2.54 centimeters. Do I have inches in my top right corner? Yes. So I'm done. I just have to do the math. So I multiply everything on top. So I have 2,000 plus 2 zeros. I have that on top. 2 times that times that times that is this. And on the bottom, I have 1 times 2.54. Put that in your calculator. What do you do?
78740.15748.
Okay. So you get that. What is my unit? Inches. Top right corner. How many sig figs do I need? 1. how do I write that in 1/60? I can't move the decimal point. I have to round, yeah. So what does this get rounded to? This is 78,740. How do I round that to 1/60?
Question. So it goes to 8.
That's going to be an 8. So I get 80,000.
Okay.
These zeros are not significant because there's no decimal place here. But I have to put them there. Because if I don't put them there, it's 8. 8 is very different than 80,000.
Yeah.
But 80,000 is the same as 80,000.0. Adding the zeros after the decimal place don't actually change the meaning of the number, but they change the number of sig figs. And so that is my answer.
Isn't there a time when we're gonna have like kilometers over meters and have to do something crazy?
Hopefully not too crazy. I think we're going to skip it today, but one of the these problems can get really wacky. This one is more difficult than anything you need to do. So I thought I already deleted this slide. You can delete it on your paper. Whether you want to rip it up, cross it out, or burn it when you get home, doesn't matter to me. You don't need this slide. Okay? If you want to do this one as practice, you can. This one is at least similar to what we were doing here. It's just a little bit more complicated. But it's more complicated than what you would need to do on a quiz or exam. Okay? So we're running short on time. Because this is harder than anything you need to do, we're going to skip it. Yes?
Do you make your tests, or are they like the department ones?
The normal exams I make. The department final exam I don't make.
Is this stuff going to be on the departmental final?
Yeah, so everything we cover is fair game for the final. They can't put everything on there, otherwise you'd be here for 8 hours. But everything that's on the final exam, we cover. That doesn't mean everything we cover is on the final exam. Everything we cover
But the
is...
stuff that we're leaving out?
Oh, no.
Okay.
No.
All right.
Do we go to the computers to do our tests, or are we?
Everything is in here. Everything is in here. And then that one's also more difficult than you need to worry about. So if you can do this one, this is about the hardest type of problem I would ask you to do on a quiz or exam. So let's spend a little bit of time talking about the homework before we do the quiz. So always your best study guide for the quiz, and especially the exams that I write, are the Canvas homework, the part A of the homework. Okay? The Wiley stuff stays in Wiley. Okay? You really want to focus on the Canvas homework. The quizzes are similar to the homework, but definitely different. The exams are not that different. Okay? The exams are quite similar to the Canvas homework. So what I like to do for the quiz is to go over the Canvas homework. Okay? Because if you understand these questions, you will do well in the quiz. It's just that they're not the same exact questions. So let me make this bigger. So, of these states of matter, which one has a definite value, but not a definite shape? Liquid. Liquid has a definite value, not a definite shape. Gas, does gas have a definite value? No. Does gas have a definite shape? No. What about a solid? definite volume and definite shape, right? And crystal was not even in, but I needed a fourth option. Okay, now these questions. It says, which of the following statements is incorrect? The way to do a problem like this is to just start at the top, read that one, say, is that one correct or incorrect? And go through them all. Burning of propane in a barbecue grill is a physical change. Correct or incorrect?
Incorrect.
Incorrect. So it would seem that we got our answer already. Because burning of propane is a chemical reaction. After you burn propane, it is no longer propane. It's a chemical reaction. Cooking of the meat on a barbecue grill until brown is a chemical change. That's correct. You're burning it. It's turning brown and it's basically burning. So that is a chemical change.
Because you're never going to get it back to the.
Right. It's a permanent color change. You can't uncook your steak. Conversion of liquid propane in the tank, the propane gas in the grill is a physical change. Correct or incorrect? Correct. That's a state change. You're going from liquid to gas. What is it called when you go from liquid to gas? Evaporation. Right? That's a state change. That is a physical change. This one's a little bit tricky. Digestion of meat by your body involves both physical and chemical changes. That one is correct. Physical, I mean, you're chewing it, your stomach is squeezing it and stuff. Those are physical changes. But then it also gets actually digested, which is a chemical change. Cleaning of the grill afterwards using a steel brush is a physical change. Correct. All you're doing is brushing it off the grate down to the bottom of the grill. It's not burning, it's not reacting, it's not doing anything like that.
Were you hungry when you made that?
I don't know. That was too long ago, I don't remember. But statistically, based on hungry versus not hungry time, most likely yes. So, turns out the first one was the only incorrect one. Combination of two or more substances that can be separated using only a physical process, or simply a physical process, is which of these? A mixture. How would you describe a compound? Two or more elements bound together. Chemically bound, yeah. So they make up their own separate
Yeah, they
new
can be
thing.
separated by like a chemical.
They can only be separated by chemical addition. Composition was not something we talked about. Substance is a very, very vague term. That just is something. A mixture is what we said. This is how to describe an element. Pure, can't be broken down further. How do you know if something is an element very easily? It's up there. So this was mixture. Without cheating. Calcium, fluorine, and magnesium, not manganese. Calcium, fluorine, magnesium. This is one of those subjective ones that you can only write a question that's as good as possible. It is a law. Underlined, italicized, and bolded a word. I try to do that. Fortunately, I don't write the final exam, so the key word is not bolded, underlined, and italicized for you in the final exam. But the key word here is always. That's a law. Okay? We're going to have a lecture later on all about the gas laws. And one of them is, when you heat a gas, it expands. How could you rewrite that phrase to be an observation? Balloon expanded when? balloon and I saw it expand. How could you rewrite that as a hypothesis? If the balloon is heated, I think it will expand. That would be a hypothesis. Probably the trickiest one, what would be a theory that went along with that? It's basically an explanation of why does it expand when you heat it. Yeah, that's the best possible explanation. Yeah. When you heat it, the molecules move faster, and we'll learn when they move faster, they hit the wall of the balloon harder, and we stretch it out. But that would be a theory. So this was a law. If you see a question like this, and you're not sure what the artist was trying to show, you can always ask me. Okay? Always ask me if you're not sure what the picture is trying to show you. I am not trying to figure out whether you know what that is. I may not directly tell you the state, but I may tell you those molecules are close together, but moving. What would that be? That's a liquid. Here they're close together and not moving, going to close together but moving. So you're going from solid to liquid, which is called what?
Melting.
Melting. What is the reverse of melting? So
Freezing.
liquid to solid. Freezing. Then what about liquid to gas? Evaporation. Gas to liquid. Condensation. Solid to gas. And gas to solid. Deposition.
I'm glad we're allowed to ask you because I got one of the water questions wrong. Because I was so sure it wasn't solid.
No, it was the first one on Riley.
Yes, I was like, that does not look like a solid.
I got in an argument with my class last semester because to me it is clearly a solid.
It does not.
But
look
they
at
all said that is not a solid. So this was no. Which of these is a physical property? Oxygen is a gas. It's just saying what state it is. It explains what it looks like, what it feels like. That is a physical property. That is a reaction. That's a chemical property. That's a reaction. That's a chemical property. And we didn't even talk about electrons yet. That can't possibly be it. But changing numbers of electrons is essentially a chemical reaction. And so the only possible answer is that one. And then this one. Which one is a compound? The fourth one. What would you call the first one? It's a mixture. I mean, you can make a case for mixture, you could also make a case for element. It's kind of weird. Because there are molecules and single atoms, but they all seem to be the same element.
Yeah.
So that's just, I would never choose that one as an answer, because that one's questionable. What about this one? That one's definitely a mixture. You have the gray elements and the black ones, both atoms. What about that one? What do you call that one? That one's an element. They're all gray, and they're all these molecules with two atoms. And the last one is a compound. And the last one, which everybody was fine on because I don't know how you could possibly get those wrong. You'd have to be the most honest person in the world in order to get that wrong. Okay. So the way we do quizzes here is I just put them up here. Now that we have rolly chairs, that's great because if you have bad eyes like me, you can just roll yourself forward so that you can see. Okay. So you need a blank sheet of paper. Normally you'll need a calculator, but you don't today because there's no numbers on the bottom. Just need a blank sheet of paper, something to write with. When you are done, you can just set it up here and you're free to go.
So this is the food?
No, that's the quiz. No.